Petrochemistry is at the core of many of the things that make up our lives today. Basic substances for the chemicals industry come from crude oil and natural gas. Processing crude, for example, gives you petroleum or kerosene, as well as liquid gas and naphtha. The latter two form the basis for what is, in effect, an infinite array of applications. But for this, naphtha and liquid gas first need to be cracked in order to release the valuable hydrocarbons. Heat breaks down the bonds, resulting in short-chain molecules. These give you ethylene, propylene, butadiene and benzene, as well as many other byproducts like hydrogen. Benzene is a chemical compound that's essential for binding elements. It helps to produce things like medication or materials for insulation. Butadiene is highly sought after. It is primarily used to make synthetic rubber. This is needed for car tires, for example, or as synthetic fibers in clothing and footwear. And yet, the majority of these substances end up being processed still further. Catalysts and high pressure are applied to produce long-chain molecules with new properties. From ethylene comes polyethylene. It is highly ductile and resistant. From gas and water pipe networks to insulation for data cables, this plastic is the most commonly used in the world. From propylene we get polypropylene. This is even tougher than polyethylene and is better at coping with heat. You can find it in car parts or medical syringes, for example. It's hard to fathom the sheer range of products made with petrochemistry. That's why it's all the more important for OMV to reuse these valuable raw materials, returning them to a cycle even after the product's life has come to an end. This results in synthetic crude or products that will still be needed in a broadly decarbonized world. Petrochemistry also helps with this.
Dow announced plans to increase ethylene and propylene production in the U.S. Gulf Coast region. Ethylene and propylene are basic building blocks that are used in the majority of Dow's products. Feedstocks. But what is a cracker and what does it look like? How does a cracker work? A cracker is a chemical complex in which gaseous and/or liquid feedstocks are converted, primarily into ethylene, in a process called cracking. A cracker is made up of many different parts, but the furnaces, compressors, and distillation columns are the three main components. Ethane and propane feedstocks first enter into the furnace tubes where they are exposed to heat. The furnaces then heat or crack the feedstocks at extremely high temperatures near 1500 degrees Fahrenheit. The reaction is very brief and lasts only 0.2 of a second. This results in very high gas velocities approaching the speed of sound. Each furnace has a heat output equivalent to about 2,000 home furnaces, and a large cracker can have as many as 10 of these furnaces. After being heated in the furnaces, the larger feedstock molecules are broken up and reformed into smaller molecules, including ethylene, propylene, and other hydrocarbons mixed together. These substances must now be separated. The mixture of gases is moved through a series of distillation columns by very large compressors driven by steam that act like engines. The distillation columns are very tall structures that can reach heights of over 200 feet. The distillation columns are made up of as many as 200 pans or trays which distill or separate the gases. Once distilled, large quantities of co-products like ethylene, propylene, and fuel gas are produced. Once it leaves the columns, the ethylene and propylene are ready to be used to produce value-added downstream Dow products.
Polyethylene, PVC, and polystyrene are polymers, also known as plastics. They are all being produced with the help of AkzoNobel's organic peroxides via a process called free radical polymerization. Let's take a closer look at how this polymerization process works and what these plastics have in common. Since polyethylene is one of the most common polymers, we will use this as an example. The raw material used in the process is ethylene, which is the monomer in this case. While monomer means one part, polymer means many parts. so polyethylene basically means many ethylene parts. But how do we get from one part to many parts? It actually takes 3 steps. The first step in the polymerization process is the initiation. When heated, the organic peroxide breaks apart in 2 radicals. These radicals start the reaction with ethylene. One free radical opens the double bond of an ethylene molecule and forms a new radical. Then this new radical opens another ethylene monomer, and this process continues, making the actual polymer. This second step is called the propagation. Now there's only one step to go to turn a monomer into a polymer: the termination. The polymerization reaction stops once the last radical on one polymer chain meets another chain with a free radical. Then they combine, and the polyethylene is finished.
this program, we'll explain the various types of processing machines used to make the wide range of plastic products in use throughout our lives. A good start is injection molding. Injection molding is used to make plastic parts using two-part molds that, when closed, are injected with melted plastic to form individual parts. Here's how it works. Material gravity flows into the injection machine's screw, where it is melted by the compressing motion of the screw and then injected into the mold to form the part or parts. The mold is quickly cooled, letting the parts solidify. The mold opens to release the parts, and the mold closes again to repeat the cycle over and over again. Molding cycles can last anywhere from 1 second for tiny parts made in tiny molding machines to minutes for large parts made in presses the size of a building. Extrusion processes use the same plastic melting operation as injection molding, but there is no mold, and the resin compressing screw rotates constantly, and product is created continuously. Extrusion uses a die, a hollow form that molten plastic is pushed through to create its specific shape and thickness. A water bath or spray chamber then cool the extruded shape and often provide pressure and/or vacuum controls to properly size the product as it passes through. Belts or cleated pullers apply smooth tension on the product and keep it moving in pace with the extruder. A cutter or saw create the final product length, or a winder creates spools of the final product. There are many variations to the extrusion process, but a mixture of extrusion and molding is found in the blow molding process, where plastic is continuously extruded into a tube shape and then clamped in a mold and blown into its shape with compressed air. It's a process that often operates in a shuttle movement with a set of molds. Each mold takes a turn grabbing a section of extruded tube, called a parison, and shuttling it to one side to blow it into a bottle shape, letting it cool and then releasing it to be filled with product or shipped. Each mold alternates with a second mold doing the same thing for maximum productivity. The same blow molding process can also utilize multiple extruders for what is called co-extrusion. Co-extrusion is used to create bottles made up of multiple layers, and each layer possesses special characteristics like suitability for food contact, an outside color for brand awareness, ultraviolet light protection for long shelf life of the product, a layer of regrind for economical reuse of scrap, and many times barrier and adhesive layers are included to separate and bond the layers for a tough, cohesive bottle. A high volume form of blow molding uses many molds mounted onto a continuously rotating wheel mechanism. The extruder creates a hollow tube, and as the wheel rotates, each of its molds will open, grab a parison from the extruder die, blow the parison into a bottle, allow it to cool, and then place it onto a conveyor, producing a continuous stream of finished bottles originating from that continuous flow of plastic from the extruder. These wheel machines can also produce co-extruded bottles containing layers designed to meet the needs of the product and to use reclaimed material for maximum economy and recycling benefits. The very popular sales of plastic bottles for carbonated beverages has created a unique process for blow molded bottles made specifically from polyethylene terephthalate, or PET. For PET blow molding, bottles are first created in a test tube shape, injection molded preform, and then, in a separate operation, reheated and blown into their final shape. This two-stage process creates bottles that we, as consumers, know to be thin-walled, yet capable of containing gaseous carbonated beverages without losing pressure or exploding, even if they are dropped. In the blown film extrusion process, thin plastic material for products like garbage bags or the sheeting used in construction, industry, and packaging are produced. A very thin die opening, which is often fed by multiple extruders, faces upward in a round shape. A tall, thin, continuous bubble is produced vertically by this process, and it's cooled as it flows upward, typically 30 feet or more, where it is then folded and brought back down and placed onto rolls or converted into popular film products.